GameSide.com. GameSide.com.
Hello, and how are you doing today? Let's look at database and records. Let's create a database to track online game user accounts. Very simple game scenario. Your game needs to track who is logged on. Duh. When the user signs up for a game, a record containing their email address, player ID, screen name, etc. is created and written to a hash table stored on the disk drive. Each time the player logs on, you must read their record from the hash table. Each time the player logs off, you must write any changes to their record to the hash table. New player account, write a record to a hash table. Player logs on, read the record from the hash table. Player logs off, update their record, write it back out to the hash table. A database is a collection of records. I've circled in the box 3 records. If 1,000 players have signed up for the online game, there'll be 1,000 records in the database. Only 3 records are shown in this example. The dots imply that there are many more records, so I have more than 3 records down here. The dots over here mean there are more fields in each record. A record is a collection of fields. I have boxed out an entire record here. Bob@yahoo.com, that's the entire record for Bob. It's a set of information that describes something, in this case, an online game player. Records in a school database would describe a student. Records in a car dealer's database would describe a car. Only 5 fields are shown in this example. Once again, the dots here imply there are more fields. For hash buckets, the number of bytes in each record is very important. How many bytes does each record occupy? A field is a piece of record. It could be a string, an int, a double. Maybe think of it as a variable. This is field 0, or the email field. For a hash table, one of the fields needs to be a key field, something that uniquely identifies the record. Email, or field 0, is a good hash table key for 2 reasons. It's unique, and people remember it if it's used as a log on to the database. Once again, a field is a piece of a record. It could be a string, an int, a double, something akin to a variable. Play ID, or player ID, is field 1, is like a customer number. The software chooses the number, and it is not shown to the user except maybe on a billing statement. This could also be a key in the hash table, but makes a terrible logon name because nobody remembers their customer number. The rest of the fields, screen name, level, money, and the dot means there may be more that make up the record. In total, they describe one player in the game. The numeric fields may be stored as numbers or ASCII strings of characters. Most important is how many bytes of data one record occupies. We're always concerned about how big each record is. How many bytes of memory does it take to hold Sue@iCloud.com's record? Creating a hash table on disk is a simple database. Let's talk database terminology. A relational database stores information in row and column format. When you extract information from a database, what we've been calling a record is a row from the database. And what we've been calling a field is a column from the database. Keep in mind we're learning databases from the bottom up. We're learning how to build a DB from scratch. We've called this record 0. In database terminology, we call this row 0. We've been calling this field 1. In database terminology, we might call this column 1. Know the row versus column terminology. By the time you get to real databases and working on commercial databases, you'll be using row and column instead of record and field. Back to hash buckets. A critical step in storing data in a hash table on disk is converting a record into an array of bytes. Some decisions need to be made before you do this. Are letters going to be 1 byte ASCII or 2 byte Unicode? Are numbers stored in integer double format or as strings of letters? Take the information in record 0 and convert it to an array of bytes. Whether these bytes are converted as an integer or a string of letters, that's up to the designer. But do decide before you start. Hard disk drives are what we call block addressable. This means an entire block or sector of data must be read or written at a time. Disk blocks come in sizes of powers of 2, typically 512, 2048, or 4096 bytes of data. You cannot read just 8 bytes of data from a disk. You must read the entire sector, say 512 bytes, then extract the 8 bytes you want. Whether you want it or not, you're going to be reading every byte that exists in a disk sector. Let's do some math. Let's make this a 128 byte record. If we have a sector size of 512 and a record size of 128, 512 divided by 128 equals 4 records. A hash bucket in this scenario says take the entire sector, divide it by the record size, and your bucket can contain up to 4 records per sector. In this case, if all 3 records above were in the same bucket, there'd still be room in the bucket for 1 additional record. The bytes per record is very important. Is it 64, 256? Is it 512? Let's do the math. Divide the sector size by the record size, and that will determine the number of records per bucket. If you had a sector size of 512 and a record size of 64, 512 divided by 64 says you will be storing 8 records per sector or bucket. But again, not all sector sizes are the same. If you had a sector size of 2048 and a record size of 512, the math 2048 divided by 512 means you'll be storing 4 records per sector or bucket. Modern hard drives tend to have a sector size of 4096. What if you had a sector size of 256? 4096 divided by 256 equals 16 records per sector or bucket. One of the first things you do is calculate the number of records per bucket. And those are 3 examples. What if you wanted to do the math in the opposite direction? How many records per sector can you have? 8, 4, 16? Once again, we'll do the math. This time, we'll divide the sector size by the number of records. If I have a sector size of 512, and I know I'm storing 8 records per sector, then 512 divided by 8 tells me those records must be 64 bytes. If I have a sector size of 2048, and the number of records per sector is 4, the math says 2048 divided by 4 means there must be 512 bytes per record. One more example, I have a sector size of 4096. I know I'm storing 16 records per sector. 4096 divided by 16 equals 256 bytes per record. You should be able to calculate from the sector size and the number of records what each record size is, and vice versa. Using sector size and record size, you should be able to calculate the number of records. Now, records may not fit exactly into a sector, in which case you need to leave some extra space in the bucket. Let's say we had a sector size of 512 and a record size of 100. What do you do? Easy. You're going to store 5 records per sector and leave 12 unused bytes. Now, why do you leave 12 unused bytes? Because you never ever want a record to cross a sector boundary. Fit as well as you can, as many records as you can into each bucket, but do not split a record between buckets. So what do we do with the remaining 12 bytes? Option number 1 says place all 12 free bytes at the end of the sector. That means we'll have records starting at byte 0, byte 100, byte 200, byte 300, byte 400. That's nice and simple. The last 12 bytes, bytes 500 to 511, will be free and unused. Option number 2 is to place 2 free bytes at the end of each record. Although we're only storing 100 bytes per record, we might want to assign a little extra data to that record, so we'll put 2 extra bytes and really do a record size of 102. Well, if we put 102 bytes into each sector, they will be located at byte 0, 102, 204, 306, 408, and we'd still have 2 extra bytes at the end of the sector at byte 512. Hash buckets. Let's create a database to track online game user accounts. The bucket analogy is straightforward. If you're going fishing, a bucket could store 4 or 5 fish if you should be lucky enough to catch that many. Heading out to the garden, grab a bucket and 4 or 5 hand tools can be placed in the bucket, and even some weeds. Buckets are handy for storing multiple physical items. Hard drives are block addressable. You must read and write entire sectors. Treat each sector like a bucket and store multiple records in each one. In RAM memory, a hash table is composed of individual slots of data. When you call a hash function of a key, it returns the individual array slot to store the key or record. In RAM memory, you don't have to worry about sectors and sector boundaries. But what about in a disk drive? A disk hash table has to be different. On the disk drive, the hash function of a key will return the sector or bucket number to store the key or record with multiple other records. See how much fatter my slots of the hash table are? I'm not going to store 1 record in sector 1. I may store 4 records in sector 1. And I may store 4 records in sector 0. And I may store 4 records in sector 2. We've done the math on previous slides. You calculate how many records will fit into each disk sector, and you make sure that you write all the records into the same bucket or sector. Here's our data again. Let's kind of step through inserting 3 records into the same hash bucket. We have 3 records, Bob, Tom, and Sue, and we're going to insert them in the database. This is when we're creating new user accounts and have to place new users into a hash table. The hash table bucket approach says insert as many records that will fit into a disk sector or bucket. If the sector size is 512 and the record size is 128, the math says each hash bucket will contain up to 4 records. So we'll go ahead and do a bucket number equals hash me and pass it the key, bob@yahoo.com. We want to insert the record for Bob into one of the 4 records of sector bucket number. If bucket number equaled 123, then we'd read sector 123 into RAM memory, insert the record for Bob, and then write that sector back out to disk to preserve it when the power goes off. Let's add a new record to the hash table. Let's call the insert method for bob@yahoo.com. Here's the record we want to store on disk. We'll say bucket number equals hash me and pass it the key bob@yahoo.com. And it was nice enough to return a 123. Store Bob in sector or bucket 123. So we read sector 123 into RAM memory, and this is sector 123 read into RAM memory right here. Sector 123 read into RAM memory. We'll linear search the bucket and right away find that byte offset 0 in the sector is free. We're going to copy the 128 byte record for Bob to offset 0 of that bucket. We'll then write sector 123 back to disk. You'll see it took us 1 disk read to load bucket 123. We changed it in RAM and did 1 disk write at the end of our insert. This is big O order of 1 insert. Hash tables are fast because you jump straight to the sector where your data is stored. One disk read, one disk write. That is an order of one algorithm. Let's insert tom@gmail.com. Let's add a new record to the hash table. Bucket number equals hash me tom@gmail.com returns the same 123. So once again, we will read sector 123 in RAM memory. This is the sector in RAM memory. We'll linear search the bucket. Record 0 is occupied, so we'll get down to byte 128. And there's a free space. So we'll insert record tom@gmail.com at byte offset 123 in the record. Once that is inserted, we'll write sector 123 back to disk. Bang. Empty records, those should be space filled. No data in here, it should be entirely space filled. Let's insert sue@icloud.com. Let's add a new record to our hash table. There it is in the red box. We want to insert sue into a database, into a hash table bucket. We'll call bucket number equals hash me, pass it the key sue@icloud.com. And once again, it returns 1, 2, 3. Insert sue into sector or bucket number 1, 2, 3. We'll read sector 1, 2, 3 into RAM memory. There's the data that's stored on the hard drive. We'll linear search the bucket and find byte 256 free. Cannot insert sue here, it's occupied. Cannot insert sue here, it's occupied. When I get to byte 256, I see a bunch of spaces. I insert sue at that location, byte 256. Once I've inserted the record into my bucket in RAM memory, I write it back out to disk, to sector 1, 2, 3. What you'll notice here is my bucket has 3 used records and 1 empty record. That was the insert operation. Let's do a find. Find sue@icloud.com. Find it in our hash table. Let's retrieve a record from that same hash bucket. Well, my key is sue@icloud. I call hash me, and it returns the bucket number 123 and says you should find sue in bucket 123. So I read sector 123 into RAM memory. There's my sector in RAM memory, not on disk, but in RAM memory right now. The record at byte 0, Bob, does not match the key sue@icloud. So I'm going to continue the search of the bucket until found, or there's an empty record located. Find takes 1 disk read. It's an order of 1. Now I'm going to change slides here, but I did not reread the bucket. The hash function has already returned 123. Sector 123 is already in RAM memory. I'm searching RAM memory. I'm not rereading the disk sector. The record at byte 128 is Tom. It does not match the key sue@icloud. We're still searching for sue, so we'll continue the search of the bucket until a found or an empty record. We're doing a simple linear search or probe of this bucket for the key that we're trying to read. Continue the find of sue@icloud. The hash function has already returned 123, and sector 123 is already read into RAM. We're linearly searching the data in the RAM memory. The record at byte 256 sue does match the key sue@icloud.com. So this stops the search of the bucket. We've located the data we're looking for in the sector that we were supposed to find it. Return the entire record at byte offset 256 to the user and say, here's the data you were looking for out of the hash table. All we're doing is a simple linear search or probe of the bucket once it's in RAM memory. Let's do another find. Let's do a find of xxx@icloud.com. We're going to retrieve a record from the same hash bucket, but this time the record's not found. The hash function is returned 123 for xxx@icloud. We've got that sector loaded into RAM memory. We're going to linear search it. We'll look at record 0 at byte offset 0 and say that's not my data. We'll look at record 128 or byte offset 128, and Tom does not match our email address. We'll look at 256, byte offset 256. Sue does not match our xxx at iCloud.com. Finally, we'll search the fourth record. At byte offset 384, there's all spaces. If you reach an empty record, that means your data is not found. Let's return a not found for xxx at iCloud. We hit an empty record, which indicates it's not in the hash table. What if this bucket was full? What if this bucket was completely full? There were 4 records in it, and none of them were xxx at iCloud. In that case, you'd go ahead and read sector 124 and see if the email address you're looking for is in that next sector. When we probe on disk-based hash tables, we probe by reading the next sector in the disk file. When there is no room, new records go to the next sector. Let's do a delete operation. Let's delete tom@gmail.com. Delete a record from this same hash bucket that we've been working on. Bucket number equals hash me of tom@gmail.com returns a 123. We're going to read sector 123 into RAM memory. We'll do our linear search for tom@gmail and find it at byte offset 128. Like many database operations, the first step of a delete is to find what you're deleting. And we just found our record at byte offset 128 in bucket 123. Delete is a find first, then remove. But we have to be careful when removing a record. We do not want to mess up the find or search algorithm. So when you delete a record, we must mark it as deleted. We're going to replace the record tom@gmail with some sort of deleted flag, not just empty spaces, but something that tells us that this is not an empty record. If we just filled this with spaces, search and insert would treat it like there wasn't anything there. We've got to make sure that we don't mess up the search. If we were linear searching this bucket, we don't want to give up here. We want to say, okay, if I'm looking for Sue, that's not an empty record, that's a deleted one. Keep looking for Sue. And of course, we'd have to write the sector or bucket 123 back to disk drive. You can see the delete operations means we have to read the sector once. We have to write the sector 1. Delete on a disk-based hash table is an order of 1 operation. It's going to take 1 read and 1 write as long as you don't have a bucket overflow. Also, with this deleted flag, you can reuse space on a future insert. If you're inserting a new item and you notice a deleted record as opposed to an empty record, you can go ahead, reclaim that space, and insert your record in that deleted record. Whew. Hash buckets. Insert, find, and delete operations are all big O order of 1 algorithms. Hash tables are very fast, and comparatively so, they're even fast on disk drive. Now, full hash buckets would mean insert, find, and delete have to probe to complete. Typically, a linear probe to sector +1, +2, +3 is used to find an open position or to find a record we're looking for. That's common, but any probe amount works. If you want to jump 5 sectors ahead and read the data in 5 sectors and probe that amount, you can. As long as the number of extra sectors read is relatively small, the hash table will keep up its order of 1 performance. Do not, I repeat, do not worry about the bucket linear search inside a RAM memory. It's the number of disk reads that you have to be concerned with. So we did a lot of operations where we had to linear search this bucket while it was in RAM. Well, that happens so fast compared to 1 disk read, it's negligible. You don't have to worry about that linear search. The linear search you have to worry about is the one that reads multiple disk sectors. That will slow down a database. Linear searching data in RAM will not slow it down. Insert, find, and delete are all big O order of 1 algorithms. Given the time penalty of reading extra disk sectors, lots of free space is a huge requirement for hash tables on disk. When the hash files fill, the system must be taken down, larger disk space allocated, and the data rehashed to make sure the probe amounts are small. If you have a hash disk table that is 75% full, it's time to bring the system down, allocate more space so your hash table becomes 40% full or 30% full. Remember, once hash tables get beyond 50% full, they start to slow down, and it is a noticeable difference. If you go to insert a record into a bucket and you have to read 6, 7, 8, 10 disk sectors to find a spot for it, that will slow down your hash table. Reading 1 or 2 sectors is no big deal. Reading a large number of extra sectors will slow down the system. The layered approach to creating a database to track online game user accounts. The trick to the hash table bucket approach is converting from a bucket in RAM memory to a bucket of disk memory. In RAM, a bucket is most likely an array of record objects, and on disk, it's an array of bytes the exact same size as a disk sector. Let's keep with our sector size of 512 and our record size of 128. To represent a hash bucket in RAM, you probably have a simple array of records. If at most you can store 4 records per bucket, slot 0 of the array contains a reference to the record 0 object. Slot 1 contains a reference to the record 1 object. We store RAM hash buckets as arrays of records. The data in RAM is stored in a very different format than the data is stored on disk drive. Let's look at a disk hash bucket. A disk hash bucket is just an array of bytes. So at byte 0, record 0 will be copied. At byte 128, record 1. At byte 256, record 2. This is just a big fat array of bytes. It's not divided up into individual objects. It's an array of bytes. So let's look at converting a RAM hash bucket, which is an array of records, to an array of bytes suitable for a disk sector. Here's an example. In the red box, we have a public class hash record. We'll keep track in each hash record, an email address, a player ID, a screen name, and an int level of the game they're on. Our email address will be the key, and the maximum number of characters in each hash record is going to be 128 bytes. I'll warn you right now, this example contains hard-coded values. It is better to use constants. If I had the room in my programming examples to declare a static final int sector size of 512, a static final int record size of 128, and a static final int bucket size of 4, I would use it if I had room. That is the better way to code. One record in memory is one hash record object. One record equals one player account. Now there definitely could be more fields in this record. All fields, however, can be converted to and from a 128 byte array. The only thing I have to be concerned with is all of this data adds up to, at most, 128 bytes. Public class hash bucket. Notice the red box around the hash bucket. One bucket in RAM is a hash bucket object. One bucket equals 4 player accounts. All records can be converted to and from a 512 byte array. Each system is different. Be flexible on the sector and record sizes. If you change your hard drives, the sector size could change. If you change your records, the record size changed. Always better to use constants, which are easy to change, than to use hard-coded values like this 4 here. The direct approach is to write 2 functions. One function to convert a hash bucket into an array of bytes, and another to convert an array of bytes to a hash bucket. So here's my hash bucket in RAM. It's an array of 4 hash record objects in RAM. I can write a function to go straight from my 4 hash records into an array of 512 bytes. That's for writing to the disk. When I'm ready to read a bucket from disk, I will read the array of 512 bytes. That's easy. And then I will convert it back to a hash bucket, an array of 4 record objects. That is the direct approach. I'm going to show you an alternative to doing it. The layered approach says put a layer between the RAM memory and the disk memory. Convert the 4 hash records to and from 4 simple string objects. Convert 4 string objects to and from a 512 byte array. This is the extra layer. I'm going to go from a hash bucket to 4 128 character string objects. I can then go from 4 128 character string objects to an array of 512 bytes. That's for writing data to the disk. When it comes time to be reading a bucket, I'll read the raw 512 bytes off the disk. I will divide the 512 bytes into 4 128 character string objects. And from the 4 128 character string objects, I will convert them back to 4 hash record objects and assign it to my hash bucket array. Do you see the extra layer that I'm putting between RAM memory and disk memory? This is RAM memory over here. This is disk memory over here. I'm using strings as a layer or bridge between the two. I'm hoping you're seeing how you insert a layer between the complex hash bucket in RAM memory and the simple byte array stored in disk. The 4 string objects are an intermediate step. Whenever presented with a large problem, you want to break it up into smaller pieces. And this breaks this problem into 2 smaller pieces. It helps to simplify storing other data structures as well. Now let's look at the function to convert hash records to and from strings. Let's use fixed length fields. We're going to copy email address to characters 0 through 63 in our array. We're going to copy and convert player ID to characters 64 and 73 in the array. We're going to copy the screen name to characters 74 to 94 in the array. And finally, copy or convert the level number to characters 95 and 98. Bobster is on level 4 of the game. These characters represent the level. Now, this isn't the whole record. There's some extra data here. It can be used any way you want. If there is no more data in the record, then this would be space filled. Space fill any unused character in a field or at the end of the string. Function hash record to string and string to hash record are not hard. You have built-in functions to convert to and from strings. If I need to convert this to a string, I'll call a built-in function. If I want to convert this back to a number, I'll call a built-in function. All you got to do is take one hash record and write it out to an array of bytes. Fixed length fields are one way to convert from data in RAM to bytes stored on disk. There are many different approaches. Be flexible. Strings as the middle layer is not a requirement, but they are easier to use and system independent. The functions string to byte array and byte array to string are trivial. A string is essentially an array of characters, and converting between a character and a byte is as easy as it gets. To recap the layer approach, we're going to need 4 functions. 1, convert a RAM record to a string. That's this line right here. I've got a hash record in RAM memory. I've got to convert it to a string of 128 characters. Number 2, we need to convert a string to an array of bytes. That's this arrow right here. I have a string of 128 characters. I want to convert it to a byte array of 128 characters. Going the other direction during a read, I need to convert an array of bytes to a string. Take a chunk of memory from the byte array and convert it back to a 128 character string. That 128 character string will represent one record in the database. Then write a string to RAM record method and you're done. Let's use this layer approach to make it easier to develop newer and powerful versions of our database. None of this is set in stone. The extra layer of strings, fixed length fields, converting numeric fields to character fields. The layered approach is just one way to split a larger problem into smaller problems. There are other solutions to this problem.
GameSci.com.